I hope you received my email. I've shared the first class transparency already, right? I have changed it a little bit from what we did in class, incorporated a little more. What we'll do is, today we go back a little bit and discuss where we had stopped, and this time with models. Yesterday, last time I forgot to bring the models. And then we move on a little bit. So today we talk about some symmetry groups. We learn how to identify symmetry point groups of molecules, no matter how complicated or how easy they are. And then what we'll do is we'll just start talking about how you can use matrices to represent symmetry operations. And the next Friday when we come back, we will see how you can take that a little further. So that is the only part. What we will discuss next day and maybe the day after is the only part where we have a little complicated mathematics. Please don't get scared. It's not really very difficult. So that is really like the activation barrier. After that, it's going to be really smooth. What we are trying to do in this course is that we try to understand how things happen, but eventually we try to work out something that would work even for dummies. Something that would be completely mechanical, and you can refer to a table and say whatever you have to say. For that, we need to do a little bit of mathematics. Please don't get scared. Okay. So to start with, I think we had closed the discussion last day with ferrocene, utherocene and ferrocene. So let us start with the eclipsed configuration. Eclipsed is very easy. So let us say these are the two rings, right? 5-membered rings, one on the top, one on the bottom. That is the structure of ferrocene when it is eclipsed, right? So let me just keep it here and see if it will project or not. So this is the eclipse structure. You don't even see the red ring because we have the black ring on the top. And I think you had identified the symmetry operations of this already. What are the symmetry operations? Let us remind ourselves. What is the highest order axis? C5. Where is C5? Here. Here, right? This is C5. Okay? You have C5. What else do you have? C2. Where is C2? Between the rings and oriented like this. Right? Between the rings and oriented like this. From an apex to the midpoint of the opposite bond. Very easy. But if I ask you how many C5 operations are there? How many C5 operations are there? There is one C5 element, but how many C5 operations are there? 4 or 5? 4, because C5 to the power 5 is just identity, right? What else do you have? Any other axis? Okay, what about plane? Two kinds of planes. First is, we can say sigma d. What is sigma d? This is sigma d, right? The vertical planes actually, but they are going to bisect the angles between the perpendicular C2 axis, so we call them dihedral planes. And we are going to have a sigma h also. Where is sigma h? Yeah, passing through the ruthenium or ferrous iron, whatever it is, and parallel to the rings. That is sigma h. Right? So what is the point group then? Why D, why not C? Because those C2 axes are there, you have to account for them. If the C2 axes are not there, then I could have called them C2H. But here, since the C2 axes are there, you have to account for them as well, so you call it D5H. Okay. Now let us talk about the other example, which is a little more complicated. What is the other example? It is the staggered configuration of ruthenocene. So we've already talked about this, C5, 5C2, 5 sigma D, sigma H, and there is D5H. Now let us talk about the staggered configuration. Okay. This here is your staggered configuration. Right? Now, what is there? Do I still have the C5? Yes, I do. Right? C5 is still there. Moreover, the C5 has now become another axis. Can you identify that axis? In addition to C5, exactly, it is S10. You see it is S10, right? Take this one, right? Rotate it by 360 degrees by 10. It is going to come here, but it will be at the top. Now if you reflect with respect to the non-existent horizontal plane, then you reach this red point. And you can work that out for each and every carbon atom that is there. Okay, so far so good? Achal? Okay. So C5 now becomes H10 also. C5, S10. Alright. What else will be there? Will there be C2? Now I think last day we had a little bit of a problem identifying the C2s, right, because the drawing was not all that great. Now that we actually have pentagons, do you see the C2 nicely or not? I just turned the whole thing a little bit. Now you see, this here is C2, provided it goes through the central ion. Okay. If I try to keep it inside the two rings here, the whole thing will become very unstable. So I won't try it. Right? No need of further amusement. But please understand that it actually goes through the central ion. Okay. Now you see that it is C2. Huh? You see the ring on the top, ring at the bottom. This is at the top, this is at the bottom, right? A C2 operation with this is going to take this atom there, that atom here, okay? Then, where will this atom go? Here. This atom will go there as well. Okay. So now, convince yourselves that you have an atom to atom mapping for every atom by C2 operation. Look at the structure and convince yourself that it works. Does it work? It works, right? Convince yourself, take your time. So that's C2. How many such C2s will be there? 5. And for each C2, how many operations will be there? 1 or 2? 1. Why? Because C2 square once again is E. Don't forget that. So that is C2. Is the horizontal plane there? Horizontal plane is gone, because what you have done is you have rotated one plane with respect to the other. Horizontal plane is completely gone. What about the dihedral planes? Do you see the dihedral planes here? Still? They are still there. Right? How many dihedral planes? 5 or 10? 5? Sure? Okay, 5 dihedral planes. Right? Anything else? Nothing else? Look carefully. Look carefully if something else is there. I. Right? Generally, I is the poor cousin. We somehow tend to neglect it all the time. Right? Axes and planes are much more glamorous. We like them more, and we talk about them all the time. But I is there. As a result of that twist that we have given to the two planes with respect to each other, now this new element I has come, which was not there for the eclipsed situation. Okay, so I is there. In fact, even I have forgotten to write the I here, it seems. Okay, so well, I gave away the answer. The point group is d5t. It's not d5h anymore. Right? By twisting, what you have done is you have destroyed some amount of symmetry because sigma h is gone. So now it goes from d5h to d5d point group. Okay? So ferrocene, I hope, is clear. Sure. Can you make out the colors? Black and red? Huh? Okay. Black is You want S10, right? So I don't need this pencil. I just draw this on the paper maybe. So this paper represents the cross section of the S10 axis. Alright. Now what happens if you give it, what is the meaning of S10? What is the meaning of C10? Why, how many degrees are we rotating? 36? 36? 360 divided by 10. If you rotate it by 36, what will happen? This black atom will come to the position of this red atom, right? But the problem is the black atom is above and the red atom is below. So if you just turn by 360 degrees by 10, that is not a symmetry operation, right? However, if you now, so this is the axis, right? This is the axis. Now if you consider this plane, which was the horizontal plane of symmetry for the eclipsed situation, now what will happen? If you deflect with respect to this plane, then whatever is on the top will come to the bottom, right? So see, what you see is that you have turned it by 36 degrees. Now it is not indistinguishable, but subsequent to the turning, if you provide a deflection with respect to the horizontal plane, then you get back an indistinguishable configuration, right? So that is S10 for you. C5, S10, okay, Cn, S2n. So this is a new symmetry operation that comes in, new symmetry element that comes in as a result of staggering, but sigma h is lost, and sigma h is something that is of higher priority. So you actually go from higher symmetry to lower symmetry. Fine. Let's move on and let's talk about tetrahedron. Tetrahedron is a shape that is very close to the heart of all chemists. If you understand tetrahedron, then you understood a lot of chemistry. And this then is tetrahedron for you. Okay. So what we did in the previous class is that we put the tetrahedron inside a box and we got a figure like this. I don't know how clear the figure is. The figure is actually from Cotton's book itself. Unfortunately, net connection was down in my office today, so I could not get a prettier picture. But I think you can figure out, right? So this is your tetrahedron. Okay. Now let us see what you have. What is the principal axis of symmetry? Huh? C3. This is C3 axis. How many such C3 axes are there? 4. 1, 2, 3, 4. How many C3 operations would be there? 4 into 2, 8, right? Why? Because you can turn once and then again you could turn once again. If you turn thrice, then you have identity. Okay? So C3 and C3 square, 2 operations are there. So 8 C3. Okay? And this is a property of what are called Platonic solids. Objects that have more than one principal axis of symmetry. So which one is the principal axis of symmetry here? There are 4 C3s, right? 4 identical C3s. After this, we will see a case where you have 3 C2s, but you can actually identify a principal axis of symmetry, a single principal axis of symmetry. Here you cannot. Here all the 3 C3 axes can act as, should be considered as principal axis of symmetry because you cannot distinguish between them. Okay? More than one principal axis of symmetry. Platonic solid, that's what it's called. HC3. What else was there? I think we discussed this in the previous class. Which other axis is there? C6. C6 is not there. C6 is definitely not there. C2 is there. Where is C2? This is C2. This is something that you can show very nicely using the model. Do you see C2? So 8 C3 operations and you have the C2. And how many C2s? That is very clear from this figure, isn't it? There are 3. So XYZ, that becomes very convenient. XYZ axis, the 3 C2 axis. 3 C2. Anything else? Yeah? Each C2 axis is also an S4 axis, right? So, how many S4 operations will be there? S4 and S4 cube. Menak? What is S4? You turn by 90 degrees, right? Right? You turn by 90 degrees and then you have to reflect with respect to this plane. Okay. Now what you could do is you could turn by 190 degrees, that is S4 to the power 1, S4 1. If you turn it twice, then that becomes a C2 operation already. Okay, and then the thing is after that you cannot reflect, but then you can turn it thrice and then you can reflect. So there are two kinds of S4 operations, right? Marcos? Huh? Okay. 6 S4 operations, 3 axes, 2 operations per axis. Alright. Sigma D, we have discussed sigma D. Where are the sigma D's? Now you see it very nicely. One thing to understand here is that you take these two sigma D's, do you see that they are perpendicular to each other? And you can actually work this out. When you put it inside a rectangle, you can work this out nicely and you can see that these are perpendicular. It's very important to understand that these two planes are going to be perpendicular, right? How many such planes will be there? 6 or 8? 6? Okay. 6, actually the answer was in front of you anyway. Sorry. And one thing that we sometimes forget, we should not forget, is that whenever we list the symmetry operations, we should not forget the obvious, and that is E. Anything and everything has E. E means identity, or C1, whatever way you want to call it. Okay. You take a tortoise and turn it around by 360 degrees, it's a symmetry operation for the tortoise. Maybe rhino would have been a better example.
So why is it necessary to list the identity operation?
Because as we will see later, when we use group theory, it is very important that we work with the order of the group. Order means the total number of symmetry operations. Now this is also a symmetry operation. If you leave this out, then you will be working with one less than the order. So we should not forget E. Okay, in mathematics, if you forget 1 for multiplication or 0 for addition, then things are not going to be all that great, isn't it? Okay, fine. So that is a tetrahedron. In fact, I asked you to work this out at home, isn't it? That how many operations are there in the tetrahedron? I hope some of you did it. Even if you didn't, the answer is now in front of you. All right. So this is called TD. And depending on which operations are there, which operations are not there, you can have variants of TD, TH, T, so on and so forth. That you can look up in your Cotton's book. Now, let us talk about my favorite molecule, allene. We just started talking about allene in the previous class, right? So this is what allene looks like. Okay, I'll take these atoms off. This is allene. Okay. So see, once again, this plane and this plane, they are perpendicular to each other, isn't it? You see that? So it's basically like you have started with a tetrahedron, okay, and somehow you have been able to pull it in such a way that you have been able to bring in a distortion like this. So I think we will understand now that allene will have symmetry operations, symmetry elements that will be somehow related to those of tetrahedron. It is just that many of the symmetry operations would have been destroyed as a result of distortion. Okay. So what are the symmetry operations that are there in allene? I can write down the first one. Okay. Now you tell me what the second one is. C2. Where are the C2s? This is a C2, this is very easy, and this is the principal axis because it's a unique C2. Do you see that this is a C2? Now, there are two other C2s. Where are the other C2s? So you see it very nicely if you hold it like this. hold it like this. Okay. Now think of what is easier for me, horizontal or vertical, maybe horizontal. Okay. Think of this axis defined by these two index fingers of mine. Can everybody see? Now if I see what you have, the one towards you on the top, look at the two atoms that are towards you on the top, the two atoms that are towards you, the top one is towards your right, the bottom one is towards your left, right? Just remember that. The top one is towards your right, the bottom one is towards your left. Okay. I turn it by 180 degrees. See what has happened? Look at the atoms towards you. The one on the top is towards your right, the one at the bottom is towards your left. Okay? You have to use both eyes. One eye is not going to help. Do you see this? Yes or no? Is that a yes? Is that a no? Yes. Okay. Sure? C2? Sumit, right? Sure? Okay. The other C2 is perpendicular to it. Once again, don't forget, look at the atoms towards you. The one on the top is towards your right. Right? Are you sure? Now turn it. You get back the same thing. Okay. So 3 C2s. 1. Then it's just that you have to hold it like this. 2 and 3. And do you notice that these 3 C2 axes are still perpendicular to each other? Isn't it? They're still perpendicular to each other. It's just that there is a long axis and there are 2 short axes. Okay? Any question? No question? Fine. So, okay, this is also S4, right? The long axis is also S4, right? Turn it by 90 degrees and then reflect. You get back the same thing. Okay? S4 and 3 C2s. Fine? What about planes? Do I have inversion? Inversion symmetry? No inversion. Start from here, go to the center, go there, there is nothing. Okay. What else? What about planes? Do I have planes? How many S4s will be there? What happens if this is S4, right? So this is 1 and this is 2. This is not even a symmetry operation. You go there, it doesn't make a difference. There is only one S4. Okay. Now, planes. Is there any other plane? There are so many planes in tetrahedron. Only 2 have survived. Okay. What will be the point group? Principal axis of symmetry is there. What is the principal axis of symmetry? C2. Do we have perpendicular C2s? Yes. So it has to be D2. And is there a horizontal plane? No. Dihedral plane? Yes. So it is D2D. Alright? So Alin is simple. You understand Alin better if you draw a Newman projection. So the way I was showing to you is basically Newman projection. You draw a circle, draw one line this way, one line that way, that is Newman projection. So it's basically Newman projection. Okay, now let us make this a little more interesting or less interesting depending on what it becomes. Let me do a little bit of substitution. If an organic chemist has to do it, maybe it's not all that easy. For me it is very easy. I just have to put in 2 white spheres. So now let us say this is the case. This is hydrogen, this is chlorine or some such thing. Okay? Substituted Alin. E is there. Is there anything else? C2? This C2? Is this C2? No. Then? Okay. What about this one? Hydrogen is towards your top, right? Turn it, chlorine comes towards your top. However, look at this one. Chlorine towards you, the chlorine is at the bottom, and towards your right. Turn it, you get the same thing. So one C2 survives, nothing else survives. So which point group will it be? C2 or C3? C2. C2. What about this? If the two substitutions are on the same carbon, then what happens? Which C2 is there? Now, the long axis is there. Right? That is C2. The other C2s are obviously not there. Is there anything else? Sigma? Where is sigma? Is this a sigma? Is there any other sigma?
Yes.
This is also a sigma. So this is C2. This is one plane. This is another perpendicular plane. Inversion symmetry is not there. E is of course there. What is the point group? Huh? C2V. Have we talked about any C2V molecule earlier? Water, right? So now look at this carefully. Forget the rest of the molecule. You have something that looks like water here. Forget this part of the molecule. You have something that looks like water here, perpendicular to each other. Okay, so even though chemically there is nothing similar between water and this disubstituted allene, they belong to the same family as far as symmetry is concerned. And then, if you think of CH2Cl2, CH2Cl2, does it not have the same symmetry? Once again, you have one C2, one plane here, one plane here. CH2Cl2 is also C2V. So water, CH2Cl2 and disubstituted allene provided substitution is on the same carbon, they all belong to the same point group, that is C2V. And here also see the two planes are not equivalent. They don't belong to the same class. Alright?